Hello Pre-Calc BC, this is day 10, number 21 homework, and oh look, it's a particle problem, just like I told you you'd see a lot of. So we have a particle moving along a line so that its position is given by this, where S is measured in meters and T is measured in seconds. And before I do anything else, what I'm going to do is I'm going to go ahead and FOIL that out. I think it's just going to be easier. I know I'm probably going to have to take some derivatives, and I would rather use power rule when I'm working with my derivatives. So I'm just going to go ahead and FOIL out t minus 2 squared is going to be t squared minus 4t plus 4. And then you're just going to FOIL that out. And just to save some time, I'm going to tell you what you get. It's going to be t cubed minus 8t squared plus 20t minus 16. So that's what you just get once you FOIL all of that. All right, so this is your position right here. Okay, so now we are finding the instantaneous velocity at any time t. Instantaneous meaning find the derivative. So s prime is equal to v, and you can say s prime of t if you want, or v of t, either is fine. And I'm just going to use power rule for that. So bring my exponent forward, 3t squared, bring my exponent forward, minus 16t, and the derivative of 20t is just going to be 20. All right, so there's part A. Part B, find the acceleration. Okay, so we should know that when we take the derivative of velocity, we get acceleration. So we're just going to take the derivative again now. Bring our exponent forward. That's going to be a 6t and then minus 16. All right, part C, when is the particle at rest? So if the particle is at rest, that means the particle is stopped, okay? Which means velocity must be equal to 0. So I am just going to take my velocity equation and I am going to set it equal to 0. And this is a calculator question. So you could just go ahead and graph this if you want and find the intersection points. This does actually factor, so I'm just going to factor it real quick. But you could just find your x-intercepts. That would be fine also. But you're going to get t equals 10/3 seconds and t equals 2 seconds. All right, and again, the reason that we set velocity equal to 0, because when we're at rest, that means we're stopped, so velocity is 0. All right, so this is probably the trickiest part of this, letter D, and it's going to take the most time. So I'm going to scroll down some more. Oh boy. In fact, I'm just going to move this over here. All right, describe the motion of the particle. At what values of t does the particle change direction? So when I do this, what I like to do is, actually, I'm just going to erase all this. I need as much room as I can get here. So if you still needed that, you can go backwards in the video and watch it. All right, so I'm going to graph both S and V. So S was, I'm going to type in what I got once I FOILed it out. Okay, I think that's right. All right, so that looks like that. And you can see that we have an intercept at 2 and then also at 4. Okay, it's like something like that ish. Okay. This is 2, 0. Just pretend that it's going through 4. The struggle is real. All right. Okay. That's going to be good enough. Okay, let's see here. And then I'm going to also, what I also found, just FYI, was it's probably good to find that minimum. Because my maximum I already know is at the 2, but the minimum would be good to find, and we'll talk about why in a minute. I'm just going to find it before I type in the other graph. So 3 1/3 and then negative 1.85. The 3 1/3, by the way, is that 10/3 that we had before when it was at rest. Okay, that really makes my graph not look great. So, okay, we'll just say that's the minimum. 10/3, that was the 3 1/3, negative 1.85. And then this is 4, 0. That 4, 0 actually doesn't really mean anything, though, for this graph. We'll talk about why in a minute, so I'm just going to leave it like this. All right, so now I'm going to graph V. And V's equation was 3x squared minus 16x plus 20. Okay, and we have an intercept at 2, 0, which I can see, and then I'm just going to find the other one. And that's that 10/3 again, 3.3330. So at 2 and at 3/3, or 10/3, excuse me. Like 3 1/3. So that's 2 and 10/3. All right, so I don't even know how long that took to get that graphed, but there we go. All right, so before we even actually write down describing the motion, we're going to explore these graphs a little bit. So what you need to remember is that when you have a positive slope on position, that means your derivative is in the positive. So take a look at this, right? This is a positive slope. That means the derivative is in the positives, okay? Now, what you have to remember here is that positive slope means your derivative's in the positive, but what is our derivative? It's velocity. So that means that velocity is also positive. What does that mean? Positive velocity means we're moving to the right or up, but in this case, we're moving to the right. Now, at 2 seconds, you're going to notice that all of a sudden, we are going downhill here. This is now a negative slope. And since slope is negative, that means the derivative is in the negatives or below the x-axis. And what is the derivative? It's the velocity. So since your slope is negative, your velocity is negative. And what does that mean? It means we're headed to the left. And again, you can see this, that we're in the negatives right now for our derivative. But then wait, at 10/3, what happens? Oh, we're going uphill again, positive slope. And look, we're above the x-axis. All right, so once again, positive slope means our derivative or velocity is positive, and we're back to moving right. Okay, so once again, I want you to notice that your mins and your maxes, so look, I had a max at 2, 0, I had a min at 10/3. So a max at 2 and a min at 10/3, and look, those maxes and mins are represented in the x-intercepts of the graph of the derivative. All right, so we've talked about almost everything we needed to, but I usually like to say where the particle started as well. So in order to do that, I'm just going to plug t equals 0 into my original S of t equation. You could plug it into the FOILed one, but it's going to be faster to do it here. Just plugging in zeros. So that's going to be a 4 times a negative 4 is a negative 16. And actually, if I had my S of t still typed into my calculator, which I don't, right? I have my velocity one typed in. You could see that your y-intercept down here was at 0, negative 16. All right, so now I'm ready to talk about the motion of the particle. I would say the particle starts at negative 16 meters, and you could say when t equals 0. Okay, and then what is the particle doing? It's moving to the right, and I know that because it has a positive slope. Okay, the particle travels to the right. And again, that's because it has a positive velocity. Okay, we can see it's a positive slope, so positive velocity, until t equals 2 seconds. All right, because again, at 2 seconds, suddenly now we have a negative slope. So that means then the particle changes directions. This is a thrilling story, isn't it? You're on the edge of your seat. The particle changes directions and travels to the left. Okay, and again, we know we're traveling to the left because it has a negative velocity. I am running out of room. There we go. A negative velocity, right? Slope is negative, and you also can see it's in the negatives. Okay, and then at t equals 10⁻³ seconds, the particle changes directions again. What is happening? This is so dramatic. How do I know it's changing directions again? Well, because at 10⁻³ suddenly, oh, I have a positive slope again. Okay, I have a positive slope here. So, I guess I'll finish the sentence. So at t equals 10⁻³ second, the particle changes directions again and travels to the right. Okay, and again, that's because I have a positive velocity. Okay, notice I did explicitly say where the particle changes directions. I actually use that terminology. It's changing directions at t equals 2 and at t equals 10⁻³ seconds. And notice I did most of my interpreting actually from the position graph, not the velocity graph. But let's go over and look at the velocity graph real quick. But just to be clear, this is what you would need to have for describe the motion. You don't need anything else there. So again, up here where I'm in the yellow, both of these locations are where I have a positive velocity, so I'm moving to the right. Okay, I know that because my velocity, my y-coordinates are above the x-axis. So positive velocity means I'm moving right. Down here in the blue, I'm below the x-axis, so this means my velocity is negative and I'm moving to the left. Okay, now don't worry about the fact that here you're going downhill and here you're going uphill. That's dealing with the slope of velocity or derivative of velocity, which means acceleration. That's something we'll talk more about on day 11. But for right now, this is all the information you need to be able to take from it. Your change in direction, again, is where your slope of position changes from a positive to a negative, or you can see that same location on your x-intercepts on your velocity graph, because that's where velocity goes from a positive to a negative. Also real quick, you can actually interpret backwards a little bit. So let me just erase all this that I just put here. So see how, oh gosh, I'm playing with fire here. Ooh, I think that's probably as good as I'm going to get. All right, so see how up here at 2, 0, you're going from a positive velocity to a negative velocity. So this means that your slope of your position went from a positive slope to a negative slope. Positive, negative. So you can actually tell, even if you didn't have this, you can tell since you went from a positive to a negative that at 2, 0, the original equation, or at x equals 2, the original position graph would have had a max. Whereas at 10⁻³, look, you're going from a negative velocity to a positive velocity. That means that in the original, you had a negative slope, and then it became a positive slope. So that means that you're dealing with a min at 10⁻³. And if you look back at the graph, even though I just erased all of it or crossed it off, you can see that's true. Okay. All right, so there you go. You got a little more than you bargained for with that question. I kind of went off on a tangent about some other things, but we'll practice this more next week. Have a good day.